I will share one incident and one of my experiences. We were all in a war room trying to do a SaaS release for our product, and suddenly our GM walks in the room. We were wondering, why is he here? Is he already congratulating us for the SaaS release or what it is? He indicated that a client service engineer is trying to set up a demo for a mission-critical client, and she is not able to work with one of the features there. And all our focus then shifted. Some of us, we took over that issue, what's the problem? And the others were still doing the SaaS release. So, just wanted to say that each one of us here at some point in time in life would have been in that war room kind of a situation, right? Where you're trying to launch, say, a mobile application, which is to be subscribed by millions of users, and there's a glitch. Or you would have undergone long cycles of planning, resources about your digital initiatives. What will be the dollar value there? So for these, we all have been undergoing some kind of a digital initiative or a modernization, so to say. And this modernization would be, say, been there since last 5 years or maybe 10 years. Each industry that we have here, public sector, healthcare, insurance, banking, retail, each of them is undergoing that initiative right now. But then there are certain common pain points that we all face. And the first one in that is that the ability to get to the issues within the system. It could be connecting to a legacy system or potentially something new. We did not do something with scale or whatever the reason may be. But before our customers are impacted, we should be able to get to those issues and resolve them. So pretty much having a very small mean time to respond. Secondly, these digital initiatives that we have, they are supposed to be kind of a magic pill or a bullet, and then they are expected to resolve every issue that is there. When most of the times, we don't even know what the environment requires. And thirdly, each one of us who is here, right, wants to reduce cost so that we can run our business optimally. Hello, everyone. I'm Swati Nanda, and I'm a software engineer at Broadcom's IMS division. And here is my colleague, Abhijit.
Hi. Good morning, everybody. I'm Abhijit Bhadra, software engineer in IMS division at Broadcom. We'll walk you through how we are helping our customers for the problems that Swati just talked about. And more importantly, we will discuss more about the artificial intelligence or data science or the generative AI stuff that we are using in our product called DxO2. Our session will be around 40 minutes long and followed by a Q&A session. So Broadcom's observability and AIOps solution is built on these three fundamental principles. And we strongly believe that if somebody follow these principles, they should be able to address any issues, any mission critical issues or anything. So how many of you have seen the application issues? Maybe everybody. But do you guys think it's really the application is the problem? Always? I don't think so. Sometimes your problem might be in the infrastructure layer, sometimes your problem in the network layer. So we need to make sure that we correlate the data from different sources and present it in a uniform way so that we can take proactive action and make much more faster decision. That's what our first principle talks about. We need to ensure that our IT operations and business goals are in sync, and they should support each other. This alignment helps us to set the right expectation. And that's what basically our second principle basically is talking about. On the third one, which is end-to-end observability across cloud, mobile, and mainframe. So in a distributed world today, we have an application running on your mobile device, accessing the mainframe data, and running on a cloud infrastructure. Now, we need to ensure that IT operations running from cloud to mainframe to mobile, they should manage and monitor cohesively. So our product, DX Operational Observability, or DXO2, are based on these three core principles. Before we go into deep into how we are doing it and all those things, let me talk about high level how this how the high level architecture of our product. So data from application, infrastructure, network, mainframe, even on the third-party products like Datadog, Dynatrace, all this data is pushed to a data lake, and in the form of traces, events, topology, metrics, etc. And in the data lake, we basically normalize, correlate, and enrich the data using different AI/ML techniques like anomaly detection or outlier detection, different clustering techniques, classification techniques, and all those things. And this helps us to build products like hotspot analysis, predictive capacity analytics, or action job recommendation, observability advisor, those kind of things. The data from the data lake also used to build other features like service analytics, cross-domain root cause analytics, and unified dashboard, etc. This data is further pushed to different automation tools like Chef or Atomic or anything, notification and notification tools like, for example, your ServiceNow or the BMC Remedy, and different collaboration tools like Slack or Team. Now I am handing it over to Shwati for further discussion on this. Over to you, Shwati.
Thanks, Abhijit. So we saw the three principles. Now let me take you over to the first one right now. So at the outset, I will talk about stream analytics and anomaly detection and how these tools are helping us in democratizing and correlating this data so that we have one pane of glass, single pane of glass across the entire product, and we're able to take proactive actions and have faster decisions taken. So stream analytics, as we all know, has helped organization to basically get the risks, issues, and even opportunities pretty quickly. So what it really does is, when the data is in motion, and before it goes to some kind of a data store or somewhere, it tries to do some processing on it. So on our product, we have data sources which are disparate, and they could be application data, infrastructure data, network, mainframes, or some kind of third parties even. And we have all sorts of metrics, topology, alarms, text data, logs. They are very meaningful and have a lot of information about how our system is doing. So we have various collectors, connectors, agents, cloud gateways that collects the data from these disparate resources. And it puts them into a data pipeline, which is streamed thanks to the technologies that we have, like Kafka, PubSub, different types of architectures that help us in doing so. Now, all this data is there in the pipeline, and the various analysis, machine learning, and artificial intelligence is done upon them. So we do features like service level indicators, objectives, anomaly detections, prediction on top of that data, capacity analytics, alarm clustering for root cause, etc. So once this data is in stream and has been acted upon, it is sent to the data lake for consumption. So this was our Kappa architecture, taking the data in flow. So any sort of analysis is done with the data in flow. Whereas in the traditional systems, they would query the data, do some kind of batch processing, and then that data would be ready for consumption in future. So we also have that batch processing layer in the Lambda architecture that does that for issues like cold start, and other things. And then, yeah, that data is also fed into the data lake. So basically, what the data pipeline is helping us with is, it is streamlining the data for us, and upfront, quickly, when the data is still in transit, we are able to act upon it and do analysis upon it. Once the data is available in the data lake, we are really, it's ready for consumption for any UI, any notification engine, or any dashboarding, any insights that we want to project for your environment. So this is a very cost-effective way of organizing the data for us here. Now, what are anomalies? There could be a sudden drop of activity in your system, or there could be a sudden increase of activity on your system. There could be a glitch in hardware, or an intrusion attack, or there could be some sequence of events that has led to a system in a very weird state. All of them might result in a low-performing system or a downtime for you. And it's not a very pleasant business experience for the clients and for yourself. So we use anomaly detection in DXO2, where we are able to analyze and get to those anomalies in the data, in the metrics that we have, in the topology. And we are able to tell about them to the customers. So we use the T-digest algorithm, and we have used the AVL tree digest implementation of it. That, by the way, works very well with the streamed data, and it's a very cost-effective way of, we don't have to store a whole lot of information there. Why? Because T-digest is a compact sketch, and then on each of the sketches, we really calculate the quantile bands. And for those bands, we really, based on those bands, we spot what the anomalies are, and those bands are with the trend, with the seasonality, those change over a period of time. We use the rate band and for our stream analytics. This kind of an algorithm, as I said, is very good for stream data. If there is any kind of a skewed data also, it can take care of it with the repeated samples if there are there in the data, and if there are ordered sets. So it gives them weightage accordingly. We can also configure alarms on these anomalies, and the users can be informed because of this. On the right top, if you look at it, that is an anomaly point, and the greens are the lower and the upper limit of the bands that we have. And at the bottom is how we configure the alarms on them. So having anomalies and bands avoids the use of user putting static thresholds as well. So that way, you don't have to change the thresholds on your metrics based on your usage. So basically, it forms the basis of static thresholding, and then over a period of time, you can work with static thresholding. When you're comfortable with the system, go ahead and configure the dynamic thresholds, and then you are all set to go, because the system understands your data now, its seasonality and trends, and can give you insights about it. If there are any anomalies, report them. So when an anomaly occurs in our system, the engine identifies those anomalies, can either notify the user, they can raise tickets in the various ticketing systems, take corrective action for it, or the other option is there could be an automation script when certain kind of an anomaly occurs, do XYZ. So we can even plug it into automation to resolve that anomalies, and eventually it'll be smooth business operations. You don't have to really care about every time this similar thing happening, this is what you have to do. So talked about stream analytics and anomaly detection. Next, I'll talk about how service level indicators and objectives and capacity analytics help in aligning the IT operations data to the business data so that we have the right expectations. So as I told, we have overwhelming data with us, and each of this data is very meaningful. So when there is an issue, we really go and look at the metrics. We can identify what the issue was, but what metrics to look, right? So service level indicators are those numbers, those metrics, those derived measures, which we define for our digital service. Digital service is nothing but a boundary of similar objects which we combine together. So, for example, you have an application. So you will have a corresponding application service that could comprise of front end, back end, database, right? And then based on that, you could define an application score, which could be your back-end services running fine, your UI being responsive, data has some benchmark, right? So we can combine all those and get a derived measure. So these are our service level indicators. And these really help us to know with the number I should be able to see if my application score is somehow going down. I can just go drill down and see what's the issue. We could have indicators based on UI. Say if a team is responsible for just the UI component and the responsiveness of the application, right? So they could have derived measures for UI only, derived measures for backend only. And then based on those numbers, they can just go ahead and see what's the problem. And because these comprise of the raw metrics of the actual devices or actual services or actual deployments, they can really go ahead and pinpoint that this was the area where the issue was. Let's take an example here. We have a F5 load balancer service, which have multiple load balancers behind it, right? And we say that it should be 90% available. What it really means that of all the load balancers it should be reachable, and the endpoints that we access those should be accessible as well. On top of it, we say for the month, we want a 99.95% of the availability. So if I have to do any kind of maintenance, or I can only take the pressure of 0.05% of outage for that particular component. So we use the raw metrics, the ping responses, and availability. Ping responses is kind of aggregated. We take out the percentage over 5 minutes, compare it with 90, get a derived measure there, and with the availability, do a Boolean AND. We get the availability score for our load balancer service, and we then calculate the service level objective number and say, okay, it has to be 99.95% of time, otherwise we calculate the error budget remaining. That is giving you an insight how many hours are left for you so that you can take that outage and be compliant. So what happens behind the scene is we have our SLI and SLO engine, and we leverage the streaming and pipelining that we talked about. So the specifications are nothing but calculations with the data in stream, and we calculate these measures. And the performance like indicators, it could be, as I said, availability, service score, calculations that we have on SLIs, and those numbers. They could be done on the context of a service, and they use the raw metrics of the components of the service. The calculations are all mathematical calculations, and then there are expression-based, logic-based, ternary operators, all are available. We can set alarms, we can set anomalies on these metrics, and user can be notified if any kind of a threshold is being breached. Then the error budget remaining number really can help you plan your maintenances as well. So there is an option where we do not penalize you for any known maintenance that you have. So we either stop the calculations of the error budget remaining when your maintenance window is on, or there is an option you can adjust your error budget based on your maintenance times or down times that you have had. Those are the known ones. And these metrics eventually participate in any kind of another analysis for like alarm clustering and root cause, etc. So this is how you configure the service level indicators. And you could use any sorts of expression-based formulas to calculate those numbers there. You can set alarms on them as well. So I mean, we have our SaaS product, so we understand these compliances are really necessary, and they are the real indicators of how our services are doing. And these indicators also comply with the dynamic boundary of the services. I mean, today I might have 5 load balancers under my digital service. Tomorrow I might want to increase or decrease them. So these SLI, SLOs are calculated dynamically based on those. And then the performance is tracked against the error budget. So you know what is the risk if you don't act upon it, what is this risk there for your compliance. We also have the views where we can actually see these numbers. So the availability, for example, there, how is it being impacted by the alarms in the system? So we have that view as well, where you can really see how the alarms are impacting the service level indicator and objectives that you have there. Next, we talk about capacity. Suppose you're trying to add very frequently new features on your product. How is it going to help your, or how is it going to impact your container environment? Or suppose your online transactions are increasing, can your network handle those? If you want, there could be some network calls that are not mission critical. If you move them to your private network, what will be the impact? Can you reduce the cost by doing so? Also, suppose you have kind of on-prem kind of a environment right now. If you want to move cloud, then will your customers get same level of performance that they used to get when everything was at their location? Oops, sorry. Right, so we have the capacity analytics engine and predictions engine that helps us do so. It can predict metric over time, and which will help you to run your business optimally so that you can put your resources based on the needs that you're expecting in future. If there are anything which is not used, you can reduce the wastages there. And the engine also takes care of the seasonality. So if a particular month you're expecting your usage to be high, it can predict your resource metrics based on that. If you need any additional resources for compute, disk, it can let you know as well. Basically, those metrics would be projected over the period of time, and then you can bring down the unused resources because it will indicate that this resource is underutilized, and you can divert the traffic if you want to. So for all this, we use regression, and we predict the data, we predict the metric values looking at what was the regression trend that was there, and we predict those values that way. Take 2 use cases here where Jack is a capacity planner at a telco. He wants to optimize his infrastructure cost, and he should be able to see what the servers that he has, what are the hotspots, what could be the potential wastages, where he has resources which are lying unused. So our DXO2 provides those hotspots and wastages, the entities which are not used, and everything is in service context, and you get micro and macro level of forecast. That being said, I mean, you could see what is happening in days' time and a week's time, then 3 months, 6 months, 1 year as well. Similarly, Rahul is a service owner with a bank and is responsible for maintaining the performance and availability of the systems at his bank, so pretty much the compute resources. Even he gets all of which Jack gets, like everything is in all the predictions, all the predicted numbers of the metrics are in the service context, short-term and long-term, medium-term as well. He can also put actionable alarms on it so that, okay, when there is like 7 days or 3 days, I mean, where the threshold is expiring, okay, he can go ahead and maybe add memory so that after those 3 days, everything is fine and working for his environment. So this is how the wheel that shows how the capacity analytics works for our product. So as I said, we have weekly seasonality forecasting and the UI that complements it. On the left here, you can see the actual versus the predicted, and you get forecasts for day, week, month, 3 months, 6 months, and 9 months. And these are at the individual device levels. And next one is it gives you a view of what are your hotspots, what are the unused entities. You could do a reset forecast as well based upon your data. Sometimes you just trying your agents and the data you might not think is as good, so there's an option for resetting the forecast as well. So here I will take a pause and tell you about the granularity at which the predictions are done. And we use the value of R square determining if the predicted value, how confident are we about that value. Now, R square is a statistical term. It's a root mean square error. Basically, how good the fit that you have, what is the goodness of the fit, and what is the variation in proportion of the dependent variable with respect to the independent variable. So essentially, whatever is the observed data, what is the variation of your model, how well it is fitting it. So we have a few models and we are adding on models every time. So we have a simple linear model, then we have a weekly trimmed model, and then we have seasonal weekly models as well, which takes care of weekly trends over a period of time. So based on each one of them, we calculate the predictions and the R-square value, and whichever gives the best R-square value, we select that prediction for you. You could also see what will be the prediction based on the growth of the metric. Say if your metric is going to increase by 20%, 40, 60, 80, whatever that number is, how will be the metrics predictions based on that? We also have, as I told you, we could put alarms on these predictions, and if any action is required, say the threshold being getting violated in, say, next 9 days, so you could keep a tap on it and then that you need to take action for it, basically. So this is what we have. So what it really does, it helps us to plan for a capacity and run our systems in an optimal way. So I talked about how we democratize the data, how we align the IT operations and the business goals. Next, how it all works with end-to-end observability. I will call Abhijit to talk about those.
Thank you, Swati. All right, so I will talk about the end-to-end observability across cloud, mobile, and mainframes. And as part of it, while I'll be talking the features like alarm clustering, action job recommendation, triage, and diagnostic, and that time I will cover like what are the AI/ML thing we are following today. And we also have started working with generative AI, and I will touch upon like a couple of use cases that real use cases which we are following with generative AI. All right, so let's start with alarm clustering first. So what's the problem? Why do you need alarm clustering? Now, suppose you are a firefighter in a city, and during an emergency, you are inundated with barrage of alarms coming, they are ringing continuously. And as a person, you know that not every alarm is signaling a major incident. There might be false alarms. There might be alarms coming on the same incident multiple times. Okay? So as a firefighter, you need to distinguish between your minor incident and the critical incident. Now, you need to ignore the minor incident and you need to put more focus on the critical incident so that you can allocate resources properly. Now, finding which one is the critical incident from like a barrage of alarms is the most challenging task for this firefighter. Similarly, the problem is with the IT operators as well. When there is a problem, they had need to deal with tons of alarms coming from their monitoring tools, application, infrastructure, log, or any monitoring tools. And most of the alarms are redundant, correlated, or periodic. And from there, basically, he needs to find out which of the alarm he should be working on and what is the kind of root cause of this particular problem. So when basically you have alarms, you can have the alarms which are coming continuously for the same incident, or these redundant alarms can cause a lot of noise into your system. Grouping those alarms means you are doing the alarm clustering, and that's where basically it helps you. When one alarm triggers multiple other alarms, for example, you have a network outage, and you might have some alarms coming from your application or infrastructure monitoring tool. So those alarms are getting correlated. Now, grouping these correlated alarms also will help you to identify the root cause of the problem. And periodic alarms happens every certain period of time. And identifying this pattern and finding basically what is the anomalous situation versus what is the normal situation, this can also help you for grouping for alarm clustering. So in short, alarm clustering will help you to reduce the noise. It will speed up your root cause analysis. It will enable you for proactive issue resolution. And most importantly, instead of working on multiple number of alarms or taking action on the different alarms, when you know that there is a group of alarms, okay, so you can just take action on the group instead of the whole lot of alarms. Now coming to the ML part of it, okay? So we do alarm clustering in two ways into our system. One is basically with automated alarm clustering. Another one is a custom alarm clustering. So first step for automated clustering is extracting the feature. Now the 4 Ws define the characteristics of an alarm, and these are the 4 Ws. That where, what, which, and when. So where represents where from this alarm is coming. So generally the host name of an alarm is what basically we are referring. Host attribute of the alarm, you get the where clause. And this is a kind of a text data. And what represents what is this alarm is all about. Generally the message section of the alarm contains this information. And this is also a text data. And which means which of the services are getting impacted because of this alarm. And this is also a kind of a text data. It's a set of text data rather. And when means when this alarm has generated or when you get the last update of the alarm. And this is a kind of a time-based data or temporal data. So this way you can see you have text data or time-based data, and you basically extracted 3 text-based features, and time-based basically there are 2 features we extract. So we'll talk about it later, but that's the way basically we extract the feature. Now once we extract the feature, we convert them into a feature vectors because we need to pass this to a unsupervised clustering. So in order to convert so there are 2 kinds of data, as I said, text data and temporal data. So text data, we convert it into a TF-IDF vectors. In order to convert it, we do few pre-processing steps. So first, we remove the stop words. So stop words are those words which are used very commonly. For example, any preposition or article are kind of a stop words. And after that, we convert this entire message into lowercase, okay, just to normalize the thing. And then we calculate the TF-IDF of that message. So TF stands for like the term frequency. Term frequency is frequency of a term in a document, and IDF is an inverse document frequency. That is importance of a term in the document. And TF-IDF is basically the product of TF and IDF. And what it actually means is, like, it shows the importance of a word in a sentence. That's what this TF-IDF does. So we have a message, and in this way, and each word get a TF-IDF value. So this way, we convert basically the text data into the TF-IDF vector. For temporal data, we extract two features. One is with the recent data, another one is a historical time data. Recent data is for 24 hours, and historical data is for last 30 days. So, and each data is represented with a bit vector. And each bit, basically, it represents the, each bit is a kind of a 5 minutes interval window. So this way, we have a recent data having 288 bits, and the historical data for 30 days is 8640 bits. Now, each bit, the value for each bit can be either 1 or 0. 1 represents that during that 5 minutes interval, that alarm was present, and 0 means it's not present. So in this way, we extract basically 2 features here and 3 features with the text data, and text data is converted into the TF-IDF vector, and temporal data is converted into the bit vector. So far, we have extracted the feature, we convert them into the feature vectors, and next comes to the clustering techniques. Okay, so you can think of it, each alarm, basically we represent it into 5 different vectors. Okay, and each vector is so in a 5-dimensional plane, it's just a point now. So now we use our hierarchical density-based clustering, which is a kind of a modified version of DV clustering a little bit. Okay, it's hierarchical in nature, which internally uses the cosine distance calculation in order to find out the close proximity of the alarms, basically whichever is in the close proximity. So they form the clusters as you can see it here. All right, so let's move to the custom clustering. So custom clustering is a kind of a rule-based clustering. Rule means, you can define the rule, what alarms you would like to cluster, and how would you like to cluster. So for example, like you are saying that filter alarms for specified time and cluster by configuration item and message. That means like you are specifying that I want to take the alarms for certain specific time and I want to cluster them with a configuration item and message. So this is around 9-10 alarms with their values of the configuration item and message, as you can see it here. And the messages are coming from different configuration item, router A, router B, router C. And when they cluster, each alarm basically gets the number out of it. Okay, you can see like first message got cluster ID 1, second message got cluster ID 4. So whoever has got the same cluster ID, those alarms will get clustered together. Now, how are we achieving it? So we have the Kafka stream. From that, we get the filtered alarms, list of alarms. And then basically we extract the cluster by and cluster by items. Like in this example, it's the configuration item and message. And then we remove the stop words and IPs and host name, make everything in lowercase. So for example, like our message, for example, unauthorized access attempt blocked from IP 192.168.1.101, that becomes like a unauthorized access attempt blocked IP. So here, from is a stop word, and we also remove the IP. So this way, like all the configuration item and all the message is converted into this kind of things. And in this way, we get a bag of words. So you have a message, you got basically different words out of it. So this way we get a bag of words, And after that, we assign each word as a number, as you can see it here. Any number, but they should be unique. And ultimately, the same data got represented with the metrics in this way. And here you can see that although the messages coming from router A are different, because of our processing, the digital representation of that data is like their message is same. And after that, it's just grouping the data. So that's how we are doing our custom alarm clustering. Okay. Now, we have alarm clusters. You can take basically certain action out of it. Either you can create a ticket, or in the any ITSM system, like ServiceNow or BMC Remedy, and tickets can be created manual or automated way. Or you can create a job out of it. Now, when basically, you can create a job in any job management system like Atomic or Shape or anything. Now think about a situation like you got an alarm which says that your disk utilization is 90%. And that time basically you would like to create a disk cleanup job. And that's something we want to repeat it continuously, like whenever the similar kind of message comes, we want to execute it continuously. And that's the basis of our recommendation engine. So it's not quite similar like how other recommendation engine works, like Netflix. For example, like in case of Netflix, it recommends you movies or your documentaries based on your interest. And once you see it, I mean, it will not, generally doesn't recommend you the same movie or same thing. It recommends you the other movies. But in our case, it's like whenever the same alarm or same alarm cluster happens, we want to execute the similar jobs again and again. So that's the kind of a difference. So our recommendation engine has three parts of it. One is like, I would say the data collector part. So here, we collect all the necessary information, whatever is needed for our model. For this, we extract the features from alarm or alarm cluster or atomic job, and also we collect the implicit and explicit feedback. Now, implicit feedback is some feedback which is given by the user itself. For example, user selects an alarm and he said that I need to run this job. So this is the implicit feedback. And explicit feedback is like when you execute the job and after that you can see the performance of the job. You might be very happy or you might not be very happy. So you are providing the feedback in the scale of 0 to 5. So all these informations are pushed to in a remediation action log, which becomes an input to our model. We call it a RAR model. And on top of it, our learning algorithm runs, which is normalized discounted cumulative gain algorithm, and which basically processes data, and it it does the normal processing like splitting the data into test data, train data, and then it generates different metrics to make sure the performance of this model remains constant, at least it shouldn't degrade. And this entire flow runs in offline mode. And because every time, whenever the new jobs comes in, the data collection, is growing. Now on the third part, whenever basically you have a new alarm comes in, they look for the RAR model and try to find out like what are the possible jobs that I can execute with. And it basically gives you that information. So that's how our entire recommendation engine looks on top. Now coming to the next section, which is triage and diagnostic. So, and let me tell you like how it's in line to our third principle, that is end-to-end observability across different different environment and different platforms. So our triage starts from an alarm or a service. Now, from that alarm, we have the technology to find out all the related component of that alarm. So if the alarm, for example, comes from an application, we should be able to like capture all the information associated with infrastructure or even the network components. And we can provide a view something like this. So this helps you to understand how the components are connected together. And although you are seeing the alarm in the application layer, what's the performance of your network and infrastructure layer? Think about like you deploy an application in Kubernetes or even in the VMware. Okay, so you should be able to see like how they are kind of related to each other. We provide metrics for the entire topology, not only the metrics who is generated to that alarm, and also highlight some of the metrics which are kind of related to the metric from where the alarm is generated, or I would say like correlated with the metric from where the alarm is generated. And we use Pearson correlation here in order to find out whether they are correlated or not. And red dots here indicates that there is some outlier in this graph. So in this time series data, we use some G-score calculation to find out if there is any outlier or anything. Logs always plays a very crucial role in order to triage and diagnostic. And mostly like if you have the logs, you will get the information like what could be your root cause and other things. We also capture different kinds of events as part of our triage and diagnostic process. And events can be application transaction event, or it can be your change events. Change events means like some attribute change event or some topological change event. Suppose a new application is deployed on a pod. Okay, so that's the kind of a change. So those things are parts of the events. And one more interesting thing is the historical alarm reference. So historical alarm reference gives you the information whether there is any history for the alarm. Whenever a new alarm comes in, the first thing comes into our mind is it something new alarm or is it I have seen it before? And this is where you get the answer that it shows you that whether the alarm has occurred before, when does it occur, is there any ticket associated with it, what are the activities happened here. So all in all, this is how basically we look our triage and diagnostic. It's not about alarm, it's about the topology, about the metrics, logs, events, and historical alarm reference. Everything constitutes our triage and diagnostic process. Once you have this information, it is easier for somebody to find out what has happened. And this is how basically it looks into our product. So as you can see, the alarm has come from a product application performance management. We can see the topology. I haven't expanded it, but from the topology we find out that there are four alarms associated with it, and we have the algorithm which can detect like based on the components which is your suspect alarm, possible suspect alarm, and what are the related alarms. And also you give the information about transaction, logs, etc. All right, so this is our last part of our presentation. So about generative AI. So we have started our journey with generative AI like 6-8 months back. And there are a few projects which is currently undergoing. And the first project basically that I will be talking about is incident summarization. So here I just spoke about the historical alarm reference. So the use case here is, historical alarm reference provides you the historical reference of an alarm, like when basically it has happened before. And think about the situation, you have an alarm, and that might have like a 10 or 15 historical reference, and and there might be 7 or 8 tickets associated with it. And each ticket can have like 100 lines of incident notes. Now for a user, it's quite difficult when they are triaging to go through each ticket, finding out what has happened and all those things. So we are using the summarization technique of generative AI, where we are passing all the information to from the incident notes, and we are just asking, okay, tell me like what's the problem and solution. It's a simple prompt. Okay, so this way we are basically providing some value. Instead of user to go through each and every tickets what has happened, at least they got a good answer, basically like concise answer, like what has happened before and what is the steps basically you have taken to in order to solve the situation. And second use case is on troubleshooting user manual guide. So documentation, product, knowledge base, user documents, everything basically we put it in a text embedding vector and push it to a vector DB. So text embedding data is basically the digital information of your text data. So once basically user asks for any question, our GenAI engine processes that request and creates some output out of it. And also user has the provision to provide certain feedback for continuous improvement. And this kind of search helps us to more accurate and relevant search result. And just because like it's not a syntactic search anymore, it's a vector search. And since this is generative in nature, so it provides more improved user experience with more helpful and insightful response. So that concludes our presentation. If you have any question, please. Yes, sir.
I'm familiar with a little bit with vector DBs, but what do you mean by vector search? The last time we talked about.
This one?
Yeah.
Vector search means like when you are searching something, like when you are searching some string, so that is also converted to vector. Okay? And before basically it actually generative AI actually searches that particular content for you. So that's what I mean. Okay. Yes, sure.
What is the data source for these application team? I understand the analytics of stitching together. What is the data source for these?
Infra side, basically you can have UIM. Okay, and there is like UIM is another tool from Broadcom who does the infrastructure monitoring. Okay, so that's the infra side. And network side, you can have NetOps or NetApp. I mean, all of them basically send the data for the network. Yeah, of course, of course.
What I mean to say, I'm expecting to have the basic wide spectrum of the view. Bringing all the data.
Yes.
Gives you the data. How an app can bring it out and see.
Yes. Yep. Yep.
Does this tool,
It has data from all of those.
Yes. Yes.
already tapped into the VMware?
So with VMware, we have an initiative where we are trying to get that data. Not yet there, but yes.
Yeah.
Merger.
It's going to accelerate.
Yes.
Data alerts.
Sure.
Thank you, everyone. And this is what we are.
Quickly. It's okay. You mentioned the digest algorithms.
Sorry?
You mentioned the digest algorithms
Yes.
earlier on.
Did I just? Yes.
Data lake, if I got that right. Are they like real time or?
Yes, so when the data is in transit, we do the evaluations of the digest, everything.
Okay.
And the beauty of that algorithm is like it is stream based.
Yeah.
Okay, so that's why basically like I mean we can do it like at runtime. Okay, you don't need to store anything anywhere. It just continuously grow and it knows the information whatever is there.
So I guess what you're saying is that you have that feedback that you get to the but are you just doing the voice corrections? Like for instance, is it looking at the prompt statement and saying, hey, this is the correct, this is not.
Yes. I mean, it's like, I mean, if you just create a prompt in ChatGPT, right? Are you satisfied with this answer? Yes or no? Okay, so we take that feedback. Okay, no means it's a kind of a yes. Yeah, this is basically we are deploying it in the Vertex AI. Vertex AI, Google's Vertex AI. Vertex AI, Google's, right.
And we are using
Yeah, Vertex AI, and for the model, what we are using is Gemini.
the base model we are using for Gemini for now. But yeah, we understand the customers could be at various, maybe on Amazon or Meta. Yeah, there is a plan for providing interface to all of those, yes.
Vertex AI from Google, that's what we are using currently. And it's a kind of a private LLM. It's not like ChatGPT, like it's hosted, right? So your customers' data will not be shared across like different, yeah, exactly.
Access your own LLM as well.
Yeah. We can't build our product like on ChatGPT kind of stuff, right?
I think that's the data center networking, it's hard for AI use cases. You should just switch it.
Yeah. All right. Thank you.
Last question with that is, have you guys done anything with, like ServiceNow has this and Splunk's kind of looking into it? When we talk about AIOps, the ability to map applications to servers. So for instance, if you move a 3-tier server, sometimes it'll break because you don't realize there's like a single server linked.
Yeah. We have that correlation. App to infra correlation is there. Okay, so no, it's like application sends the data, infrastructure monitoring sends the data, and there should be some common in between them, right? And since we are a kind of we get all the information, okay, we can kind of like correlate the things and we can stitch it together. Okay, so you can able to see for example, you have a Java application running on a VMware. Okay, now you have an application monitoring tool which is monitoring the Java app, and your VMware is monitored by something. Okay, let's just take our DXO2, that particular platform. He can see both this data. So you can able to see this application has a sublet component which is running on this particular VM, which is part of this ESX server. Okay, so this entire thing you should be able to see.